All right, so this next example kind of comes with a nice visual that gives you something to think about when you're interpreting what this transformation actually does. So this is referred to as a projection, and it's in particular, it's the projection onto the x1 axis. This image that you see here, this is straight out of the textbook, and let's zoom in a bit and kind of break things down a bit. There's two vectors that are drawn on here. The first one, this is just the standard basis vector E1, and the second one up here, this is just the standard basis vector E2. Rather than labeling them as E1 and E2, they're just labeled as the actual column vectors if they're written as column vectors. And if I were to draw them as position vectors, like arrows here as I am right now, going from the origin, well, you could see that those two arrows, they kind of determine a square, right? If I were to draw the parallelogram rule, like as if I was going to add these two vectors, well then the parallelogram that I get would in fact be this exact square. This is referred to as the unit square. And sometimes it's helpful if you really want to wrap your head around what a transformation does, it helps to think about what that transformation is going to do to the unit square specifically. And then that'll help you figure out what it's going to do to everything else. So, okay, well, what's happening over here? What happened? It looks like, let me actually add one more thing to this picture. I'm going to draw just an arrow to indicate. This is telling you what the transformation P is doing. It takes vectors from this picture and turns them into vectors from this picture. So look at what happened to the square. It just got completely squished down. Completely squished down to the x1 axis. And actually over here it's telling you what P did to each of the standard basis vectors, E1 and E2. They're labeled in red over here, so I'll label them in red over here as well. This is P of E2. Oops, I didn't leave myself enough space. Let me move that back a bit. This is P of E2, and this is P of E1. Notice that P of E1 is the same as E1, right? E1 and P of E1 are the same. Because E1, if you draw it as a position vector and look at the point that it points to, that's already on the x1 axis. So if you push it all the way down to the x1 axis, it's not going to move. So that's why you still, P of E1 is just equal to E1. But P of E2, well, that's just the origin now. Well, and why is that? Well, look at E2. Look at the point that E2 points to. It's the point 0, 1. If you push that down to the x1 axis, like straight down, you're going to get the origin. So that's why P of E2 is just the 0 vector. Okay, and you can see with this unit square business, they've drawn a little fish in here. It's a nice picture that kind of none of the sides look the same. So there's a whole bunch of transformations that are outlined very nicely in section 1.1. I recommend you take a look at the textbook. I forget the exact pages, otherwise I'd tell you. But that fish picture really helps you see what each of the transformations do. Some of them are shears, compressions, dilations, or sometimes referred to as stretches. There's reflections and all those different all those different transformations. If you have the fish drawn in the unit square, really just any kind of image that's not symmetrical, it really allows you to see what exactly the transformations are doing. So I recommend taking a look. I've included a couple in the notes here, but you can see it's just squishing everything down into the x1 axis. So you've lost, once you apply that projection, you've lost a lot of information. It's impossible to go the other way and recover that information. And let's take a look at what I mean by that. So I'm going to zoom back out here and we'll consider some of these questions. So part A, find the standard matrix. Well, we already have done the work for that, because remember, to find the standard matrix, you just need to figure out what the transformation does to each of the standard basis vectors, and we've already made those observations. So for part A, I'm going to start up here just to leave some space. So our matrix A, the standard matrix, you don't have to call it A, by the way, I'm just going to call it A. We're going to write it as the first column will be P of E1 and the second column will be P of E2. So you're going to get 0, 0, pardon me, no, I had that backwards. P of E1 is 1, 0, and P of E2 is 0, 0. Okay, so that is our answer for part A. That's our standard matrix. Okay, so for part B, is P 1 to 1? Well, so in other words, if you start with two different input vectors, are you guaranteed to get the same output vector? Well, think about what P is doing. What is P doing? It's taking a point and it's flattening it down against the x1 axis. Is it impossible to have two different input vectors that get sent to the same output vector? Well, no, I mean, you'd probably think the answer might be no. Because look at this one, P of E2, where did it get sent? E2 was up here, and it got sent down to the origin. But nowhere, like, well, why did it go down to the origin? Well, because this projection pushes things straight down onto the x1 axis. But notice that it didn't take into account how high up E2 was, right? E2 pointed to the point 0, 1. What if it had pointed to a point way up here, way taller? The same thing would have happened. It still would have gotten moved right down to the origin. So that's kind of leading you to think that if the height of the vector is not taken into account, that probably the answer is no. Probably there's going to be more than one point mapped to certain output vectors, and indeed that's the case. So let's spell that out a little bit more. Let's look at some concrete examples. And in fact, I'll avoid using the origin just because that can always seem like an edge case. Let's take a point. I'll zoom in over here. Let's take a point here. If you apply P to that point, it's going to push it down onto the x1 axis. And if you take a point down here, P is going to push it up to the x1 axis to the point directly above it. So what if I just did this? What if I took 2 points, one of which was directly above the other? Then what's going to happen, if I apply P to both of those points, it's going to push this one down to the x1 axis, and it's going to push this one down to the x1 axis. And the output vector is going to be the same point in either case. So that's the idea here. But let's make some specific vectors. How about we take, let's try P of 1, 1. That's this point right here. So what is P going to do? It pushes it straight down to the x1 axis. Let's actually use our standard matrix, though, just to show this precisely. So we have P of 1, 1 is going to be, here's our standard matrix, multiplied by the vector 1, 1. And what do you get? Well, let's actually work this out carefully. The multiplication definition, you'd have 1 times 1, 0, plus 1 times the second column, 0, 0. You just end up with 1, 0. Okay, well, what if I took a point directly above that? How about I just increase the second coordinate by 1? I'm going to get, this will be 1, 0, 0, 0, multiplied by the vector 1, 2, and we get 1 times 1, 0, plus 2 times 0, 0. That's what you get if you work out the multiplication there. And what's that going to be? Well, it's just going to be 1 times 1, 0, plus 2 times 0, 0, which is just 0, 0. So if you add the 0 vector to 1, 0, you just get 1, 0. And this, now we have our answer definitively, right? 1, 0, and 1, 0. They both gave the same output vector, but the two input vectors were different, right? For that reason, so since, let's write this formally. Since we have 1, 1 is not equal to 1, 2, those were our two input vectors which were distinct, but P of 1, 1 equals P of 1, 2, because they both were equal to the vector 1, 0, that's exactly enough to refute any claim that P is 1 to 1. So we can say P is not 1 to 1. Okay, so that is our fully rigorous answer to part B. And then what about part C? Is P onto? Okay, so that's the question. Is P onto? Remember what onto means? I can scroll up a bit. Onto means every vector in the codomain has to appear as an output vector from that transformation somehow. Well, what do all the output vectors of this transformation P have in common? Well, what does P do? Remember, it pushes everything down onto the x1 horizontal axis. So really, that's your answer right there. It can't be onto. right? The only vectors that appear as output vectors are the ones that are directly on the horizontal axis. But if I take any vector up here, I'll zoom in a bit so you can see. If I take any vector, say up here, that's not on the horizontal axis, well, I can take that as an input vector, right? I can plug that into P, and it'll go down to the x1 axis. But I can't ever get points like this as output vectors from P. The only thing I can get from P are points that are on the horizontal axis. So for that reason, that P is not onto. So let's be concrete here. Let's come up with a specific point that's not on in the range of P. That's what we're really talking about here. We want to find a point in the codomain R2 that's not in the range of P. So let's take y equal to, how about the vector 1, 1? In fact, any vector that has a second coordinate that's not equal to 0 will work. We'll just show that this is not equal to P of x for any input vector x. So for any vector x in R2, I'll write it in general as x1, x2. We can say that P of x1, x2, what's it going to look like? Well, it'll be the standard matrix. This is why it's good to find the standard matrix of a transformation, because it allows you to evaluate the transformation at any given input point. So let's work this out. Oh, wrong one. I want to put x here, not y. So if I plug in the vector x, I'm going to get what? We'll have x1 times 1, 0 plus x2 times 0, 0. So that's going to be what? You'll have this, oops, what happened there? This will just turn into 0, right? You've got x2 times the 0 vector. x2 is just a scalar. The result is going to be a 0 vector. So this whole term is just going to turn into the 0 vector. Over here, you're going to have, well, x1 times the vector 1, 0. You're going to have x1, 0. Okay? So that's your output vector. No matter what x1 is, this will never be equal to the vector 1, 1. Right? So that means y, this vector y that we came up with, will never, ever be an output vector from the transformation P. So for that reason, it's P is not onto. So therefore, let's be really clear and say y, this vector here that we picked, and again, anything that had a second coordinate that's non-zero would have worked. We didn't have to pick this vector, right? So y is not in the range of P. So P is not onto.